Hi, welcome to Algebra 2 Common Core. Today in Lesson 5, we're going to work on solving equations that involve fractions. So in our first example, we see that the beginning equations both are proportions. A proportion is just a fraction equal to another fraction. So we can just use the technique of cross multiplication to solve those fraction equations. So in the first example, I'm going to say let's multiply the 5 times 4x plus 5. And then go the other direction, so 2 will be multiplied by x minus 1. This is a nice, easy equation to solve. I've got 20x plus 25 is equal to 2x minus 2. Subtracting 2x from both sides, that gives me 18x, and I can also subtract 25 from both sides, so that's giving me negative 27. Divide both sides of the equation by 18. So I now have the solution x equals negative 3/2. Now we want to make sure that when we go back to the original equation, we don't get any denominators that are equal to 0. That would be undefined. This is clearly not true because both denominators are numbers. We can check this solution by storing the solution negative 3/2 into our calculator. So remember how we put in negative 3/2 store x, and then type the left side of the equation and get the answer, type the right side of the equation and get the answer, and make sure that the answers match. And in this case, I see on my calculator that yes, this is a true solution. Let's go ahead and do example B. So we're going to cross multiply because I've got a proportion. X plus 1 times x minus 6 is equal to 2 times 2 minus x. So on the left side, I'm going to double distribute or use FOIL. So that gives me x squared minus 5x minus 6. On the right side, 2 times 2 is 4 minus 2x. Now, this is just a quadratic equation, so let's put it in standard form. I'm going to subtract 4 and add 2x to both sides of the equation so that I'll have the equation equal to 0. So in standard form, I'm starting with x squared minus 3x minus 10 equals 0. This is factorable, so x minus 5 times x plus 2 equals 0. Quadratic, so I can t-bar it and get that x is equal to 5, x is equal to negative 2. Now at first glance it almost looks like that negative 2 is going to make my denominator of the first fraction be 0, but that's not true because I've got 2 minus x. Now I want to check both solutions, so I'm going to start with 5 and say 5 plus 1 over 2 minus 5, does that equal 2 over 5 minus 6? On the left side, I'm getting 6 over negative 3. On the right side, 2 over negative 1. Yes, those are equivalent to each other, so x equals 5 works. Do the same thing with negative 2. So negative 2 plus 1 over 2 minus negative 2. Does that equal 2 over negative 2 minus 6. So on the left side, I'm getting negative 1/4. On the right side, 2 over negative 8. And yes, those two fractions are equivalent. So both of these solutions are solutions to the original equation. If I found one that did not work, I would of course reject it. That would be called an extraneous solution. Now in the next set of equations, I see that I don't have a proportion. You've got a couple options. If it's easy enough to rewrite the equation by combining fractions, you could make it into a proportion and still use the method of cross multiplying. That might be true of example A. But I'm going to solve by our second method, which is going to be to multiply by the least common denominator of all of my denominators. So looking at A, I'm looking at my denominators and I'm going to say, oh, my least common denominator of these fractions would be a 4x. All of the fraction denominators go into 4x. So notice how I'm going to take the whole equation and I'm going to multiply the whole thing by 4x. As long as I do the same thing to the left side and the right side of the equation, I'm going to preserve equality. So on the left side, I'm going to take that 4x and I'm going to multiply it by the first fraction and the second fraction. Same thing on the right side, I'm going to multiply by the fraction on the right. My goal here is to eliminate denominators. So 4x, when I multiply by 1 over 2, the 2 and the 4x cancel, leaving me with a 2x. So 2x times 1 is 2x. Take that very same 4x and now multiply it by the second fraction, but this time the denominator completely cancels, so 4x and 4x cancel, leaving me with just a negative 9. On the right side, the same exact thing happens. This 4x cancels with that 4x, and I'm left with a 3. This is a really easy linear equation to solve, so add 9 to both sides of the equation. So notice how I have really simplified this equation by eliminating those denominators. So 2x is equal to 12, x is equal to 6. Now this again would be a nice example to just store 6 in my calculator, type the left side, type the right side, and make sure that the check works. Clearly, 6 is not going to give me an extraneous solution because it's not going to make my denominator undefined. So 6 does turn out to be the solution here. Let's try the same thing for the second example. So looking at these denominators, I'm going to say 6, 10, and 15 all go into, the smallest number they all go into would be 30. So I'm going to multiply both sides of the equation by 30. Again, notice how I'm doing the same thing to the left side of the equation as I am to the right side. So I'm going to multiply 30 times this first fraction on the left and the second fraction. So in the case of the first fraction, 30 and 6 cancel. That leaves me with a 5, so I'll multiply 5 times x minus 4. In the case of the second fraction, the 30 and the 10 cancel, leaving me with a 3. So I'm going to take that 3 and multiply it by x minus 2. On the right side, 30 and 15 cancel, leaving me with a 2. 2 times 31 is 62. So go ahead and distribute on the left. So I've got 5x minus 20 plus 3x minus 6 equals 62. So I've got 8x minus 26 equals 62. Add 26 to both sides of the equation. So 8x is equal to 88. X is equal to 11. Now let's go ahead and look at that check. 11 minus 4 over 6 plus 11 minus 2 over 10. Does that equal 31 over 15? Well, I've got 7/6 plus 9/10. Does that equal 31/15? Let's make everything have a denominator of 30, so multiply the first fraction by 5 on the top and the bottom. Let's multiply everything by 3 for the second fraction. And on the right side, let's multiply by 2. And I see that, yes, 35 plus 27 does equal 62. So my solution is x equals 11. So let's take a look at the steps that we used in order to solve these equations with multiple fractions. Now take some time to please fill in your notes, so you might need to pause the video. Our first step to solving these rational equations was to decide what is the least common denominator of all of my denominators in the equation. When I find that least common denominator, I'm going to multiply every single fraction by that least common denominator. Remember, our goal was to eliminate fractions. So when I multiplied both sides by the least common denominator, I distributed where possible and always ended up canceling my denominators. If you don't end up with cancellation, then that means that something went wrong when you found your least common denominator. So my goal here is to do this cancellation of denominators. The resulting equation should be a much easier equation to solve. I'm either going to end up with a quadratic equation that hopefully will be factorable, or I could end up with a nice easy linear equation where I'll only get one solution. It's necessary on these problems to check all solutions and make sure you always go back to the original equation. So what we would then want to do is reject any extraneous solutions. Reject any solutions that don't work in the original equation. Usually those extraneous solutions will make the denominator equal 0. So we don't want our fractions to be undefined. So any that make the denominator equal 0, we're going to automatically reject. So pause the video if you need to copy down these steps, and then we're going to try a little bit more challenging problems on the next page. So in exercise 3, it says solve each of the following equations for x. So I look at both denominators. You'll notice that on the right side, this has a denominator of 1. And I notice that my least common denominator is going to be x times x minus 2. So I'm going to take my whole equation and I'm going to multiply the left side by x and x minus 2 and the right side by x and x minus 2. And again, on the left side, I'm going to have to distribute times the first fraction and the second fraction. So I'm using that same x and x minus 2 to multiply by both fractions. In the case of the first fraction, the x minus 2's will cancel. So that's going to leave me with x times x, which is x squared. In the case of the second fraction, the x's will cancel. So I'm going to have x minus 2 times x plus 2. On the right side, I don't have any cancellation, so I'm going to have to multiply 2 times x and then multiply that answer by x minus 2. So let's simplify the equation that we have. X squared plus, do your double distribution, and we get x squared minus 4 equals, on the right side, 2x times x is 2x squared. 2x times negative 2 is negative 4x. So clearly on the left side we have 2x squared minus 4, but on the right side we have 2x squared minus 4x. So when we subtract 2x from both sides of the equation, it's not quadratic anymore. I have a nice easy linear equation, so negative 4 is equal to negative 4x. Dividing both sides by negative 4, x is equal to 1. Now go back and look. 1 does not make my denominators undefined, so it looks like I'm going to have a good solution. But do always go back and do the check, whether it be on your calculator or by hand. 1 over 1 minus 2 plus 1 plus 2 over 1, does that equal 2? Negative 1 plus 3 does equal an answer of 2. So that checks, and yes, x equals 1 is our solution. So looking at example B, before I can find my least common denominator, I'm going to have to factor that second denominator. And I see that the factors are x plus 3 times x plus 5. So my least common denominator here has to have an x plus 5, but also has to have an x plus 3. So I'm going to take my whole equation and multiply by x plus 5 and x plus 3 on both the left side and the right side. On the left side, with the first fraction, the x plus 5's cancel. So I'm going to have to multiply the x plus 3 in my least common denominator by that numerator, x plus 1. In the case of the second fraction, both factors cancel, so that leaves me with just 18. On the right side, I see that the x plus 3 is going to cancel, so I'm going to multiply 9 times x plus 5. So do your double distribution. So x squared plus 3x plus 1x gives me plus 4x plus 3 plus 18 equals, on the right side distribute, so 9x plus 45. Put this equation in standard form, so I'm going to be combining a lot of terms here. 4x minus 9x is negative 5x. 3 plus 18, that gives me 21, but then when I subtract 45, that's going to give me a negative 24 equals 0. I'm going to continue over here with my factoring. So here's my equation again. And this quadratic I can easily factor into x minus 8 times x plus 3 equals 0. Doing your t-bar, I get x equals 8 and x equals negative 3. Now, I see that negative 3 clearly has to be rejected because that's going to make both my second denominator and my last denominator be undefined, because when I put negative 3 in for x, I get a 0 in the denominator. So the only answer I'm going to check in the original is my 8. So 8 plus 1 is 9 over 13 plus 8 over 8 plus 3 is 11. 8 plus 5 is 13. So 11 times 13, does that equal 9 over 11? And I would just type that into my calculator, and I see that yes, those two sides are equivalent, so x equals 8 does work. Now I'd like you to take a few minutes and try to find the least common denominator on C, and go through and multiply both sides by that least common denominator and see if you can solve part C. Come back and check your solution with mine when you're done. Check your work with mine. I factored the first denominator into x plus 6 times x minus 2, which did turn out to be the least common denominator. Go ahead and multiply that least common denominator by all of the fractions to cancel denominators. So in the case of the first fraction, I'm left with a 4. In the case of the second fraction, I have to multiply x minus 1 by x minus 2 because the x plus 6 is canceled. And in the case of the right side of the equation, I had to cancel the x minus 2's and keep the x plus 6 times 1. Put your equation in standard form, so that's x squared minus 4x equals 0. This factors into x times x minus 4. And as you can see, neither 0 nor 4 gave us an extraneous solution, and they did end up both working in the original equation. So I have two solutions for this problem, 0 and 4. In our last example, we're going to take a look at some application problems for rational equations. So example 4 says, Anne and Maria play tennis almost every weekend. So far, Anne has won 12 out of 20 matches. How many matches will Anne have to win in a row to improve her winning percentage to 90%? So let's take a look at what she has won so far. If she has won 12 out of 20 matches, when I convert that over to a percentage, well, first a decimal, 0.60, and then a percentage, right now she has a winning percentage of 60%. So the question says, how many matches will she need to win? So I'm going to let M be my variable representing the number of matches that Anne must win. So if I start with our original proportion, actually it's a ratio, 12 over 20, she's going to take her 12 games that she's already won and add a certain number of wins. But that also gets added to the number of games that the two of them play. And we want that ratio to equal 90%, so 0.90. Now, this is a nice proportion, so we can go ahead and cross multiply. 12 plus m would be equal to 90% times 20 plus m. Go ahead and distribute, so 12 plus m is equal to 18 plus 0.9 m. Let's subtract 0.9 m from both sides, so I get 0.1 m on the left side. Subtracting 12 from both sides, I get equals 6. And then multiply both sides by 10, or divide both sides by 0.1, and we see that she needs to win 60 more matches in order to get a winning percentage of 90%. So that's quite a few matches that they have to still keep playing. Let's check that work. 12 plus 60 over 20 plus 60. That would be 72 over 80. And if you convert that over to a percent, that is 90%. So we have found the number of matches Anne has to win. Now we're going to say that she's at that spot. She's at 72 over 80. And now we want to know how many does she have to lose to come back down to 50%. So that's going to be even lower than what she had to begin with. So we're starting with her 72 over 80. And this time we're going to say, let L equal the number of losses. Now, when we're calculating her winning percentage, I'm going to say, well, we're at 72 over 80. And if we then add on losses, the losses only get added to the denominator because her top number stands for her wins. So we want that percentage to be only 50%. Again, we can go ahead and cross multiply because this is a proportion. So 72 times 1 is equal to 50% times 80 plus L. So go ahead and distribute that 0.50. So that's giving us a 40 plus 0.50 L. Let's solve for L by subtracting 40 from both sides. So 32 is equal to 0.50 L. Multiply both sides of the equation by 2 or divide by 0.50. And L is equal to 64 matches. So again, let's check this to make sure it's giving us the correct percentage. 72 over 80 plus 64. And again, we're only adding the 64 to the denominator because the top number is wins. And if she's lost 64, she's not winning any extra. So 72 over 144 does give her a winning percentage of 50%. So 64 matches is how many she then had to lose. So you can see that this application represents a rational equation. Pretty easy rational equation, but the setup might have been kind of tricky. We'll take a look at a lot more examples of rational equations in class. Have a great night, and we'll see you next time. Bye-bye.